Okay, so I suppose any announcements before we get started? Central tendency, I just went ahead and pushed it back a day. It was due tonight. Central tendency is going to be due tomorrow. Some of the problems are a little bit more engaged as we slowly start to transition from really conceptual ideas to more, I suppose, numerical problems that require us to put things in a calculator, for example. And so some of those might be a little bit more engaged than previous homework, so you have an extra day. Dispersion, also have it set for Sunday as well. So the section on dispersion due Sunday. And really that's it in terms of due dates. So those are the next two to be aware of. Does anyone have any questions for me before we get started on the new material? If not, let's go ahead and get started. Okay, so we're moving on to measures of dispersion. So measures of dispersion, it's another measure to describe data. So in this chapter, now that we have data collected and even sometimes modeled, the previous section, we started talking about measures of central tendency, which talked about pretty much the types of ways to measure the middle behavior of the data, or in more technical terms, the typical data value. But sometimes just because there's an average to a data set doesn't mean that every data set with the same average behaves the same. You could have a bunch of test scores in between 70 and 80, and their average would be 75, roughly. And then a bunch of test scores between really 60 and 90, and the same idea. There is a certain spread that we want to consider here as well, the spread from the mean, which we call dispersion. And so there are three different types of dispersion we'll talk about today. One of them should be a little bit more obvious, the range. So the range, that one should be familiar. The other two may or may not, depending on how recently. If you have at all taken Math 105, you may be familiar with the standard deviation. And really the variance is the third one, which that one's a little bit more new, but really the variance is just the standard deviation squared. So it's not something completely new. And so we'll start off with the range. We'll start off with the easy one. And so what the range is defined as, it's just the difference between the largest and the smallest. So going back to grade school, it's the difference between the largest data value and the smallest data value. So you measure all of your data, or you collect it all, you find your smallest one, you find your largest one, you subtract one from the other, you get an answer, that's the range. And this tells you the dispersion of data relative from the smallest possible point to the largest possible point. So you're all familiar with how to compute the range, so I'm not going to spend any time on that. Instead, I pose a question. Is the range a resistant measure? So remember, resistant, I defined that the last class period. That means if you throw in an extreme value, either extreme low value or an extreme high value, does that affect the measure? So you're saying yes. And it turns out the range is a resistant measure. Actually, I'll switch the wording. It's not a resistant measure. Okay, I can convince you all why it's not a resistant measure. What it means to be resistant is that when you throw in an extreme value, the value doesn't really change that much. So imagine if not a resistant, I should probably finish that sentence, is not a resistant measure. And some example we'll consider off to the side. Imagine if we had a data set, very simple, 0, 1, 2, 3, 4, 5. Then you'd say, okay, the range, hopefully you can all see what the range is here in this problem. It's just 5. It's the largest minus the smallest, which is 5. Now what happens if I threw an extreme value in here? What would be an extreme value? Someone want to give me an example? Be an extreme value here.
Well,
What's more extreme than 12? Really extreme.
74.
74, there you go. So resistance is this idea of throwing in an extreme value. What's the new range now? 74 minus 0 is 74. Notice the range changed significantly. It's that significance that shows us that the range is not resistant to extreme values, because the range is based off of what could possibly be an extreme value. It's based off of two values, the smallest one and the largest one. What does it mean for a value to be extreme? It's either super large or super small. So this is not a resistant measure. And off to the right here is an example why. So it's not a resistant measure. So really, in practice, we don't like to use the range too much. Sometimes it's helpful to get an idea of, well, what interval the values are all going to lie in, well, what the width of that interval is. And so instead, the standard deviation and the variance are both used to determine this instead. And so, and the reason why those are better forms of dispersion is because they're based off of every data value. Every data value. And we'll start off with the standard deviation from a more conceptual idea at first. And we'll move into its formulaic interpretation. The standard deviation. So it measures the spread of the distribution relative to the mean. So it actually gives us a bit of a tool to explain, and we'll talk later about what kind of value it's actually interpreted as, or what that value actually represents. But in its most general form, the smaller your standard deviation, the values get closer to your mean. The larger the standard deviation, the more your data values are spread out from the mean. And so with this kind of conceptual idea, we can already start to answer questions that are really correlated with, well, graphs. And again, here's a histogram. And we can go ahead and look at some of these. So with that definition in mind, we want to match each one of these. So these are 4 different data sets, and we want to match each one of these to the corresponding collection of summary statistics. So A is going to correspond to 1, C is going to correspond to 1, B, and D. And the way we do this is, well, notice how the standard deviations, some of them are wildly different than the others. So there's a standard deviation that's really, really small, the 1.8. So what does that mean? It means that the values are going to be really close to the mean. Now, all of these graphs have the same shape, but the dispersion can be measured or evaluated with different scales. What I mean by this, notice for graph C, the values go from what looks like, that looks like it would be 13 at the lowest. 23, 43, so it goes from 13 to 23, as opposed to another graph that goes from, that's 47 to 57. Notice even though the graphs are relatively similar in their distribution, one of them is zoomed in a lot more than the other. And we can use the range to help us determine that. So that range gives us an idea of what the spread is, what the distribution is. And so we can correlate this idea to trying to match one of these with its corresponding graph. And for A and D, let's see, that would be 32, that goes by increments of 5, 31, 30, 21, 28, 27, 82. And then the last one, that one also goes by 5, 40, 37. So it makes sense that the one with the largest range should have the largest standard deviation because it's got a lot of ground to cover. And likewise, the one with the smallest range should have the smallest standard deviation because it has the least amount of ground to cover. So here, since C seems to have the largest spread of data, I would say C would correspond to the summary statistics in row 4, just because row 4 has the largest standard deviation. That corresponds to there's a lot of data values that the standard deviation has to cover. And likewise, the smallest range seems to be answer choice B, which then I would say it's I, because from 47 to 57, in comparison to the rest of these, that the smallest values for which the standard deviation has to account for in relation to the mean. It's a lot closer together to some central value. So if anything, that's how this conceptual idea of a standard deviation can help us have this intuition towards understanding histograms and bar graphs. So now we need to decipher between A and D. Because the unfortunate thing is, well, these are two fairly similar graphs, and the standard deviations that we have left. So we took care of that one. We took care of that one. The standard deviations that are left are too close to call. An 11 and a 10, those are too close. So we need to use another means of deciphering the two graphs. And notice how in row 3, they have a mean and a median of 53. Of course, the top one is a mean and median of 60. So perhaps we can use the distribution of the histogram to, I guess, correspond or determine which one is which ultimately. So I think it's clear, though, that this distribution here, there seems to be a maximum a little bit past 52. And then for the other one, it tends to be values closer to at 62. So I think the color schemes that I wrote down correspond exactly to the rows. So the one in purple, that one's 3, because that one matches our mean and median a little bit more appropriately. And similarly, answer choice D would be 2. So this is how we can use just the concept of standard deviation to at least decipher between the spread of data for various data sets. This is done quite a bit when comparing data sets. Sometimes you want to see, perhaps you're evaluating several people's performance and you can measure out their performance on a histogram. They all have the same mean average of, say, hours worked, or even some productivity metric, but the spread may be much more different, and the more spread means less consistency because there's more spread in the data, which means that these values can range wildly. Does anyone have any questions before we move on? Okay, brings us to a question. Is the standard deviation a resistant measure? So is the standard deviation a resistant measure? Start with that question first. You say it's no. You say it's yes. Jordan, you got a shot? You want to take a shot at it? So what you're saying, so what are the people who are saying yes, what are you saying? And if you're saying yes, it's resistant, I know. What does that really mean? What are you saying when you say it's resistant? What does that definition mean? So
like if we have like an outlier or whatever, a higher number, it doesn't affect everything.
Yeah, so ultimately, if you throw in an extreme number, so the people who said yes, this is resistant, what you're saying is if you throw in an extreme number, then the standard deviation is not really going to change that much. It's kind of hard to hear what.
If it's dependent on the median and mode, the standard deviation.
The standard deviation is based off the mean.
Exactly. So if you took an extreme value, the mean will change and the deviation will change, so it's not resistant.
That's a good thought process. We're going to go with that one. This is not resistant. Another simplified way you can think about it, I'm going to detour right fast. So I actually highlighted it. They involve every data value. The standard deviation involves every data value. If you throw in an extreme value, guess what? The standard deviation will include that extreme value. which means it will be affected by that value as well. Remember the median was resistant because the median only cared about the number of things and not the magnitude of things. And you can ignore those formulas at the bottom of the screen right fast. Those get a little intimidating for some people at first. So, and normally I'll notate the standard deviation like that. I'll write that quite a bit. The standard deviation is not resistant. And we could say it's based on every data value. But another perfectly sufficient way of thinking about it is exactly what you said. If the standard deviation is based off the mean, and the mean is not resistant, then guess what? Standard deviation is not resistant. Okay, that's one question. What do you think a standard deviation of 0 represents? Just trying to think about that one. Standard deviation of 0.
Wouldn't that just be the mean if it was 0?
Actually, yes. Whichever virtual person said that. So what they were saying, if you didn't hear it, was wouldn't that just be the mean? So to clean that up a little bit, a standard deviation of 0 means there's no spread in your data from the mean, which means every value would have to be the mean. So this would be if I interviewed everybody, if I surveyed everyone in this class and asked how old you were, you all said 19. There would be no spread of data whatsoever. It would be the same value getting picked. So that's what a standard deviation of 0 represents no spread from the mean, i.e., every data point is the mean. So it's basically you do a survey and you get the same answer every single time. So I thought that was a pretty interesting question. Okay, so that little cliff note I have right below what I wrote, the standard deviation is based on the deviation about the mean. The deviation is just the difference between a particular data value and the mean. So if, let's say the average age in this class was 19. Is anyone here 20? All right, you're 20, I'll use you. So let's say, so as we can already see, that would be a horrible average, but any case, let's say it was 19, your age is 20, the deviation is simply the difference between any data value, such as your age and the mean. 20 minus 19, 1. That's the deviation. The only reason I say that, the sum of the deviations about the mean always equals 0. So if you see that pop up in your homework, now you know how to tackle it. So deviations, so every data value has a deviation from the mean. You take whatever value you belong to, subtract that from the mean. And so now we get to this weird looking formula. Actually, two formulas, and they're very, very similar. There are two pretty similar formulas to determine the standard deviation. And it depends on whether you're looking for the population standard deviation, which means the population standard deviation means you know every data value for every person in the study that you are doing. If you're studying all students at Southeastern and you're able to say go into LeoNet and figure out every single student's height, that would be population standard deviation. You don't have to go out and survey clusters of people. And that formula, and we're actually going to work out a small example of these formulas, or at least one of these formulas. But these formulas, you're taking deviations from each data value, you're squaring them. So the deviations is the difference from the mean. You're squaring those, you're adding them together, you divide by the number of samples, and then you take the square root of that. And really the only difference between this one and the sample standard deviation is instead of dividing by the number of samples or the number of data values, you simply divide by the number of data values minus 1. That's the only difference between these formulas other than just symbolism. But in essence, it's still deviations about the mean. And also notice that the notation, any Greek life people in here? What's that symbol? The symbol right here. Greek life. That's sigma. So that's sigma that represents the population standard deviation, and then just a regular old S for sample standard deviation. I was thinking about for the first test, whenever that comes up in a few weeks, I'll just let you use a flashcard or something, and you can write whatever you want on the flashcard. I don't care. And one of these formulas may be something you might want to write down. And everything else here is just notation. So remember, this weird looking U shape, that's mu. We talked about that as the population mean in the last section. And then X with the little bar on top was the sample mean. So notice that means the same thing. It's just the context for which you are looking for the standard deviation. And so those formulas seem kind of intimidating. I do want to ask another question though. Based off of these two formulas, do you think the standard deviation can be negative? So you think to yourself, okay, I put all of this either in the calculator or whatever the case may be, and then I get an answer. Can that answer be negative? If so, why? And if not, why not? There's only one reason why you would go one way instead of the other. Actually, there's a few different ways you can think about it. Kyle, got any ideas?
No, it can't be negative because it's getting squared.
That's one way you can look at it. There's squares going on. And what happens when you scare stuff? What happens when you square stuff? It's going to become positive. No matter what the difference is, if you square -3, it becomes +9. That's one indication. But then there's the square root. And the square root can never output a negative. It took me for college algebra, I said that quite a bit. But square roots you cannot square root something and get a negative unless you're taking a class far beyond this one. But in a statistical perspective, either way will be perfectly fine. You will definitely get definitively positive values from the squares. So the standard deviation cannot be negative. And really, that's all I'm going to write. So I think that's another homework question, so keep that in mind. And from there, I can also go ahead and quickly define the variance. And the variance is another measure that people sometimes use. Sometimes people like to use the standard deviation. Sometimes people like to use the variance. The variance, though, is whatever the standard deviation is to the second power. That's it. That's all there is to it. It's not a new formula. That's why the variance here is so bland in its presentation. It's basically, some people don't like the square root part in the formula. Some people just are nitpicky about it, and they like looking at things without that square root in the formula. So some textbooks you use, they like to define the variance first and then the standard deviation, and some flip it. Our textbook, standard deviation first, which I'm okay with. And so from there, we're going to use the sample variance and standard deviation. Pen's messing up. Second. Okay, let's try it again. The sample variance and standard deviation of the following data set. And they give us 5 data points. So I'm going to scroll down to where the sample standard deviations on top. We're going to be using that formula for the sample standard deviation. There's a problem in your homework where they'll ask for the population standard deviation. So that formula will come up at some point in your homework. But what this means, we do have a data set, and I'm going to open up the calculator to figure out the mean. We need to know the mean first. We're computing this, we're going to compute this by hand at first. But we can figure out the mean using the calculator. Or you can figure it out by hand. It doesn't matter. We need the mean. And this is going to be, we're going to use the sample mean because we're looking for the sample. As you can see, it's messing up right now. So we're going to use the sample mean. And you can find that whichever way you'd like. There's only 5 data values here. You could just punch it into the calculator instead of doing the one variable summary statistics. I think I'll just do that. That's pretty straightforward. There's only 5 values here. Divided by 5. 11. So now that we have the mean, we can figure out the standard deviation. So the standard deviation, it's the square. Well, we start off with the square of the deviations. So what we're looking for, the standard deviation is lowercase s. There's a giant square root symbol. And then what this means with that parentheses x1 means what's the first data value? I see 20. Okay, so 20 minus whatever the mean was, 11. then we square that. And we do that for every single data value. So what was the next data value? It was 13. Now we find the difference between 13 and 11. So this is going to be a very long square root. And then what was the next data value? That was 4. So then the difference between 4 and 11. And then the difference between 8 and 11. And all of this is being squared, by the way. Then the difference between 10 and 11. So we are taking the deviations, the differences between the data value and the mean, and we're squaring them simply to make them positive. I mean, that's mainly why they use square in this case, to make all of those positive, and there's behind the scenes reasons why as well. And what we're dividing all of this by, because remember, there's a fraction here. It's n minus 1. N minus 1, well, lowercase n is the number of data values, 5, but then we're subtracting 1. So you can do this incrementally in your calculator if you choose. I like to do the numerator first. Square. Or if you could put it all in at once, it's perfectly fine. Minus 11. Quantity squared. And on a test, I could be completely justified in asking you to do a standard deviation by hand. If you took 105 last semester, you do know that we can do this in the calculator, and you can use the calculator to check your work. But if I ask that question, I would like to see your step-by-step process. Plus. And 8 minus 11, that's obviously, -3. If you wanted to do simplification like that, you're more than welcome to. Plus 10 minus 11 quantity squared. 144 is the numerator. We can divide that by the denominator, which is 4, 5 minus 1. And then we take the square root of that. And that is our standard deviation, our sample standard deviation. And then to figure out the variance, well, we want to figure out the sample variance, which is s squared. But all we do is square the previous result, which was 6. So we found the sample standard deviation and the sample variance by hand. Again, you may be asked to do this by hand, which means you will need to be comfortable with this formula. And there are 2 or so homework, there's actually 3 homework questions that want you to do this by hand. This may be good to attempt to make sure you are comfortable recreating this formula. But just keep in mind, though, if they ask for the population standard deviation, you won't have 5 minus 1, you'll just have 5. Just notice that formula is slightly different. They don't have a minus 1 in the denominator. So the denominators are slightly different. So just keep that in mind. Does anyone have any questions up to this point? If not, go ahead and move on to the next page. And the obvious note now is for larger data sets, we use the aid of technology to help us determine the population and sample standard deviation. We're not really going to focus on the calculator giving us the variance. We could, but it's not relevant at this moment. And so you might already see there's a data set, and I mentioned the word technology, so you might already be thinking about where this data is going to go. So a marketing firm is hired by Target to predict the amount of money a typical shopper spends at Target during just a usual visit. They do they take a systematic sample of 20 shoppers, and they ask to see how much they spent on their receipts. And here's some of the values that came up. And so with all of these values, we're just going to go ahead and determine, we'll determine both the range and the sample standard deviation of the data set. So hopefully you remember, so from last time, we talked about how to find the mean and it was the mean and the median. We're going to do the exact same process to figure out the range and the sample standard deviation. So let's remember how we found the mean. It's the same exact process. Stat, edit, and then we start typing in values. If you already started doing so, great. If not, go ahead and do so. Four. Okay. Type all the values in. You would figure out the standard deviation and range the same way you would the mean. It's the same process. So after we do that, we can quit out, go back to stats, and move over to the one variable statistics that we found in the previous section. Keep pressing enter until stuff pops up. Did anyone also get those answers? So like for the mean, did you get 33.88? You got that. So now the question is, all right, which one of these represent the range? Well, let's just start with the range. I don't see the range on here. But they make this very easy for us. They don't give us the range, but they do give us the maximum value, and they give us the minimum value. So we can figure out the range on our own, because that's just a simple subtraction. The max value is 66.01. Minimum value is 7.23. So we can figure that out pretty quickly. So we'll come back to that. 66.01 minus 7.23. And we get 58.78. That's the range. Let's go ahead and pull up the one variable stats again. So remember, we got that from the maximum and the minimum. They don't give us the range as a straightforward value. They give us the max and the min, though, and we can figure it out just going one step further. Now the sample standard deviation, so the notation we use for that is lowercase s. And what that corresponds to, the value that this corresponds to is s of x in the calculator. It's the value that says s of x. That is the sample standard deviation. And that value, because there's a lot of values here, that value is 17.401. Let's just round to 3 decimal places. Actually 2, because this is money. So let's round to 2 decimal places. 40. So that's the standard deviation here. So this does give us a measure of the spread of data from the mean. And again, we'll see what this spread of 17.40 represents. If you were a student in my 105 last semester, you might remember that this corresponds with the 68, 95, 99.7 rule. You remember that thing, or if you took 105 last semester, that's what it ends up associating with. So does anyone have any questions about part A? If not, part B says, well, suppose they just went into the computers and figured out the population standard deviation to be $25. Did our sample overestimate or underestimate the population standard deviation? Because remember, what a sample does in general is it gives some sort of inference towards to what to expect about a general behavior. So that $17.40, was that a good, or did that underestimate the amount of money a typical shopper spends, or did it underestimate? And it underestimated because it's smaller. That's it. So underestimated. Wow. Wow. Because so the population standard deviation is denoted by sigma, and that's greater than the sample that we found. This, or in other words, or if you want to put this in wording, the sample is smaller than the population, so it underestimated. Part C says, well, now the marketing firm just wants to see the spending behaviors of customers that finish shopping before 8 a.m. So I looked it up. Most Targets open at 7 a.m. So they want to see what that first hour of shoppers' behaviors are like. And let's just say the first row in the data set represents those spenders. What's the new sample standard deviation? So guess what we get to do? We get to go back and edit our list. And we only want the top 5. It's the top row. So delete. You can press the delete button right here if you want to get rid of it entirely. So yeah, you just keep clicking delete and delete. So you just get down, or you could just clear the list and type in the 5. But from here, just figure out the new sample standard deviation. And the new sample standard deviation, well, it's SX in the calculator. There is a reason why they put the X that I'll get into later. But that's $20.43. And then part D simply asks, well, does this overestimate or underestimate? Again, it's going to underestimate because it's smaller than the population standard deviation. Does anyone have any questions about this? If not, so there's going to be a few questions, and you might have already noticed this with the measures of central tendency, that sometimes they'll give you two data sets, and you'll have to compare those simultaneously. Now, one thing you could do is do one data set, figure out its answers, write those down, and then do another one. You know, you erase that list, and then you do another list, and you get a whole new set of data, and you write all of that down. Or you can do it all at once in the calculator. You can analyze two data sets at once in the calculator. How do we do that? Well, the next page in the notes actually describes that step by step, and we'll do it here as well. So in the previous section, you might recall that one of my examples, I put down a bunch of grades that I got from a 105 class that I may or may not have taught before COVID and after COVID. And I only put down 18. I cleared them up a little bit just for purposes of demonstration. So these are two different data sets that we're just going to compare side by side. And we're going to determine the range and standard deviations of these. Now, instead of doing, well, you could put one data set in, figure out all those values, but my math lab's going to alternate a lot. So you'd have to do one, erase that, do the other, and then you realize, oh wait, now it wants me to go back to the original. So instead, we're going to start off, ultimately we're going to be using the two variable statistics in the calculator because we'll have two data sets. So we're still going to go to edit like we did before. Clear that. And the first list is going to be the first data set. I'm going to be busy typing in everything from the before COVID category here. Really should have put a lot less data values here. Oh well. 89.11, 6.92, 63.37, 88.71. And then after you do that, you're going to take your cursor and go to the right. And now you're going to start filling in the L2 column in the calculator, the L2 column. And that's going to be the after COVID-19 category. So now you can start plugging in values there. 7.21, 79.8, 12.61, 2.38, and just keep going. definitely want to make sure these two lists have the same number of values too. Right, as they both stop at the same spot, you definitely want to make sure that's the case. If not, the calculator is not going to allow you to do this. So what we have done is we got up to this point in part 3, if you're looking at the notes. If you're still typing in, there's all of that. So once you type everything in, so hopefully I typed in everything correctly, you're going to quit out of this, and you're going to go right to, instead of 1 variable stats, just 1 more down to 2 variable stats. And keep pressing enter until you get something that may look familiar on the surface, but if you scroll down, you're going to have a lot more options. There's going to be these Y's all of a sudden. And what it's doing, the X's tell you information about the first list, and the Y's tell you information about the second list. So there's your simultaneous analysis without having to go back and forth. And did people get those numbers? I'm going to trust you did. So from here, so now we're at, oh, okay, well, that's good because that's what I got last night. And so, as I mentioned, the values that with an X refer to the first data set, and the values with a Y refer to the second data set. And so as I wrote down here, the range of X, remember, we're not given the range immediately, we have to figure it out. But they do give us the max and the min. So notice the max is 95.67 and the min is 6.92, and that's exactly what I have written down at the bottom of the notes here. And then the standard deviation for the first list is, well, denoted by X. And if you scroll up, you will see that that is in fact 70.69, and I rounded 3 decimal places for no reason, 692. And then if you want any information about the second data set, you look at the Y values, and they're notated the same exact way. There's an S next to the Y, so that's why they put those variables next to the symbols to distinguish in case you have more than one variable or data set being analyzed at a time. And so you can do this in general for any time. So if you're still working on the measures of central tendency homework, I think there's a problem or two that has 2 data sets. And if so, you can use this exact process just for the sample means. And they do not give the median though. I did notice that they do not give the median. You'd have to figure that one out on your own. That's a pretty helpful tool. Does anyone have any questions before we move on? If not, we're going to look at something I alluded to earlier. So now we're going to actually describe what the standard deviation is telling us, because on first glance, the standard deviation is just some number. But what does that number mean? What is that number telling us? And what it's really telling us is the proportion of values that lie within a certain interval of the mean. Because remember, the standard deviation is based off the mean. The standard deviation tells us the percentage of values that lie a certain distance from the mean. And in particular, one standard deviation from the mean holds approximately, and that's in both directions, it holds approximately 68% of the data. So that would be a more typical interval. 95% lie within 2 standard deviations, and then 3 standard deviations is 99.7%. So chances are if you lie outside of 3 standard deviations, then you're either really good or really bad, depending on what the metric is and what side of it you're on. Because that means if you're on the good side of it, it means you're better than 99.7% of people in some category, maybe like an IQ or something. And if you lie within 1 standard deviation of something, that means you're just pretty typical. Generally tends to be the case with grades in a class. So grades in a class generally look like this for the most part, if you apply it to a histogram. And so it's I guess fairly typical that 68% of students will lie within normally the mean that a lot of classes get is like mid-70s. The standard deviation always varies though, depending on what the class is. So art's probably going to have a much smaller standard deviation than math, because math grades spread out a lot. People get A's and F's, but art, I think that there's more consistency there. And so notice this is a diagram I got from the book. I thought it was a very good diagram. Not only does it characterize 68% of the data within 1 standard deviation, but it also breaks up these sections into segments. So each segment also has its own percentage that it represents in terms of proportion of data that this segment holds. And we'll talk about how to analyze this actually with the next problem here. So, example 5, we're going to analyze the average resting heart rate per minute of all of us. The average resting heart rate. So all of you are hopefully resting and not completely, just got done with a jog. I wouldn't imagine so. So if you can go ahead and participate here, what I want you to do is find a pulse somewhere of your heart, neck here, wrist, the 3 main places, and you can either count for 15 seconds, the number of beats, 30 seconds, or a minute. Whichever one you do, multiply that by 4 or 2 or nothing. Figure out the beats per minute. I'm going to start it at 9:04 on the dot. Wait another 20 seconds. Okay, well, I did mine for 15 seconds and I counted 18. So I just multiplied that by 4 to get a minute. Mine came out to be 72. What are some of the values you all got? At 84?
80.
80?
80.
80?
89.
89?
83.
Oh, 83, gotcha.
88,
88,
72.
72,
82.
82. For the person who's 72, are you a runner?
Yeah.
You're a runner? Okay, yeah. That's, they say people who do cardio, stuff like that, tend to have lower heart rates. And then virtual people, yeah, if you haven't done so already, awesome. Let's see. 81, 49, 52. Okay. 49, 82, 52. Get some more. 74, 74, 80, 80. 4, 74, 80, 80. And if you want to go ahead and start, I'm going to be putting all these right into the calculator. So if you wanted to start typing in whichever ones you can see right now. 87, 90, 86. 87, 90, 86. 87. Okay, so we're going to be taking all of these values, plugging them straight into the calculator. And also, if you have a resting heart rate of over 100, that's not good. And you need to see probably a primary physician as soon as you can. And it's clear. Okay, where am I at here? 2, 4, 87. 3, 6, 8, 2, 2, 2, 49, 2, okay, we have 19 values, it looks like. Cool. So from here, the first question they ask is, what's the mean and standard deviation? So we're going to just use one variable statistics. We only have one variable. So the mean, and we're going to assume, so sometimes the notes will do this, or the homework rather will do this, where it'll just say the standard deviation, and we're going to just use I guess for this purpose, I suppose we'll use the notation that matches here. So we'll use the population. I'm going to use the population. Is that right? I'm trying to remember what the homework used. Actually, the homework just tells you it. They'll just tell you the number. So there's no ambiguity. We'll use the sample. That's fine. It doesn't really matter here. We're going to analyze it the same exact way. But in the homework, they will tell you the standard deviation is 20. The mean's 100. There's no ambiguity there. They'll just tell you. So the mean is about 77.68. And then the standard deviation, again, I'm just going to use the sample, which is SX in the calculator. And in fact, they're very close together, so it's not really going to change too much. Do 87. So now we're going to think about, what does this mean? What does a standard deviation of 10.87 mean? Well, we can look at it in one way. About 98% of resting heart rates will be between which values? So 68%, if we scroll up a little bit to this empirical rule, as it's called, 68%, it says it right where I'm about to highlight, 68% are within one standard deviation. So how do we find the values or the boundaries of one standard deviation? Well, the lower bound of this is the mean, which was 77.68, minus the standard deviation. So that's how we're going down one standard deviation. We take the mean and we subtract the standard deviation once. And that is 66.81 for the lower bound. And then the upper bound, try to leave that, give that a little bit of space. So the upper bound, so this would be one standard deviation above the mean. So instead of minus, we use plus. 10.87, which is equal to whatever the calculator tells us. $88.55. For part D, I kind of have to create this one myself. So the first one I want is what percentage of heart rates are between 55.94 and what's the other one I want? 99.42. And then that's actually going to come right down here as well. And actually here, the lower one. So that fills in all those blanks. So there is a reason I picked those numbers. What we're trying to do is figure out how many standard deviations each one of these values are. And once we do, it gives us a metric for which we can transpose to this graph. So 55.94, how many standard deviations is this from the mean? So in other words, if we take the calculator, the mean is 77.68. And its first value of 55.94 is 21.74. And if we divide that by the standard deviation, 2 standard deviations, or how many times will we have to add or subtract the standard deviation to get that number? This is 2 standard deviations below, and this one's going to be 2 above. The only reason I mentioned 2 is because now when we look at our chart up here, here's the mean. 2 below is right here. 2 above is right here. Oh, come on. 2 above is right here. Where do they meet at? 95%. That's how you read this. You did this in 105, and we're doing it again here. That's 95% here. How many is less than those 2? Well, less than those 2, it's the sum of all of those. 0.15 plus 2.35, that times 2, and that's 5. It's the sum of everything I circled. That's 5%. And then the final one I'll do in red, because that one's here and that one's here. We add all of those together. Whatever that sum is, go ahead and jot that down. 13.5 plus 34 plus 34 is 81.5%. Once you have all of those down, you are good to go for today. Homework for measure of central tendency is due tomorrow. The homework for measures of dispersion is due Sunday. That's all I have for today. Have a good day.
You too, have a good one.